All right. Well, thank you very much. Thank you very much, John and Judy, for your nice words. And thank you for letting me do this. I'm very excited about it. I've been excited for 3 months when they told me the date, right? When I was department chairman, at the end of each semester, each semester of plan design, she would ask me, "Are you coming back next year?" And I kept coming back until she became dean and so on. Okay, I'd like to dedicate this lecture to a very good friend, Rafael Juan Torrena. He was invited to this lecture, but he passed away 5 weeks ago. And he got a PhD from this department. And later on, he became a priest. And he came to work in Baton Rouge as a chaplain of the Hispanic Apostolate. And he did an excellent job for 12 years. And then he would say that he would just apply his engineering know-how to his job as a priest. Okay? That's why he was so successful, we would say. Anyway, it turns out that, we are asked to pray for those who pray for us, to pray for each priest each day, and the priests are assigned alphabetically a date, right, for people to pray for them. And today was the day to pray for him. Wow. So I asked those of you who are so inclined to say a prayer for him. It's a coincidence or a God incident, like a friend of mine calls. Anyway, so this is my lecture, and I hope that you enjoy it and that you learn something. It's going to be homework. Okay, why 54 years in the chemical engineering department? Okay, and gratefulness. Wanted to give back. I arrived here in the spring of 1962 with no money, no source of external support. Okay? Just one loan from the federal government, $500 a semester. But at LSU, that was enough to pay for tuition, out-of-state fee, this room, not the board. I mean, you have to eat at the cafeteria. But you try to keep your cafeteria expenses and the books expenses lower. Like my goal was to spend less than $2 a day for 3 meals. I was achieving it. Okay, I was lost a lot of weight. But I was achieving it. Okay, and it's not only me that is grateful. A lot of other Cubans arrive here in the same condition. I want those of you who are present here to stand up. Okay, Cubans who arrive here in the same conditions that I did. They're grateful because the professors, Jesse Coates, Frank Rose, Bernard Pressburg, James Corden, and Arthur Keller, they really taught us very well, sent us in very successful careers, okay? And so we're very grateful to them. Arthur Keller was a recognized international authority on the sugar process. And after a while, he gave me a job, 12 hours a week, $1.25 an hour. And I was able to splurge, go to the movies once for $1. I saw Ben-Hur at the theater. So this professor really led us into great careers. Out of our group, 3 vice presidents of major companies came out. Al Lopez at Exxon, and René Sayavin at Hess Oil, and Juan Medina at the Gusa Chemicals. I invited Juan Medina, but I understand he's not in good health. Okay, so he couldn't come. Okay, now okay, anyway, they were very successful, and these people were very successful. If you look at the wall right outside this room, with the people contributing to the building of this building, most of the Spanish names there are Cubans that were grateful to the department and the college, because some of them are not engineers, to the college for the education that they got, and they became very successful. Okay. Right. So I think that we're all very grateful. So that's the reason I spent 54 years here. Okay. Now, I want to talk about highlights of my career in 3 phases: analog hybrid simulation, computer process control, and then plant design. Okay. Analog hybrid simulation, my first expertise. How did I get this expertise? Okay. The beginning. A computer device was given to me put in my office at Dow. Okay. My boss, Charlie Jones, he see what happened here in 63 when I graduated. NASA was using analog computers to train astronauts to go into space and then to infinity and beyond, or maybe just to the moon. But the chemical companies like Dow decided that they wanted to do the same thing. They were using automation and they wanted to test automation techniques on the processes and use analog computers to do that and to train the operators on using those automation techniques. So my boss, Charlie Jones, decided that I was going to be the one to do analog computation at the Louisiana division of Dow. He gave me this device, an analog computer, and put it in my office. Probably the first person in the world with a computer in his office. He was out of school. Now, this is an analog computer. It has 15 amplifiers. No, it's anyway, this, do I have? Oh, okay, it's right there. These are vacuum tubes. Most of you don't know what a vacuum tube is. You've never seen one. Those 3 vacuum tubes represented an amplifier that was a computing device, and then you programmed it here with capacitors and resistors and wires. Right. So I had it in my office. I started to play around with it to solve differential equations, stuff like that. And then something great happened. I met Paul Morrow. The second semester after I graduated, I took a course from him at 5 o'clock in the evening in automation. He had graduated with his PhD in the same graduation. And of course, I'm very happy that Nancy and his son John are here, right? He taught me the course in the evening, and he had just gotten his PhD in the same graduation I got the bachelor's a year before. Right? So he taught me the course, and then in the summer, first course in automation. It was in mechanical engineering because there was no automation course in chemical engineering, and I think he had joint appointments for the 2. So that summer, Dow hired him to give the course in the evenings to the employees there, right? And I took the course and I brought the computer with me. And when we talked about responses of controls and things like that, I would program them and show to the class what he was talking about. And because I was missing my carpool, he would give me a ride back to Baton Rouge. And in those rides, he told me, you must come back and get a PhD. Okay. And I said, no way. I have 2 babies. Ronnie was a little over a year old, and Bernie was 1 or 2 months old. Right. My mother and my wife, I kind of do it. He said, look, I did it. I have experimental verification that can be done. I did it, and he says, when you have a step change in income, right? The step change in expenditures goes immediately. It's a step response. No delay. He said, no way. So it took me 4 years to follow his advice, okay? Cecil Smith that graduated with me and went to work for Dow for a year. A year later, came back and got a PhD in record time and became a member of the faculty. Okay, he couldn't come today either. He's in Taos, New Mexico. Okay, so that was a great happening. I didn't do it at the time. My first project at Dow, that's how I got my expertise, okay? Run a computer in the Texas region because Dow didn't have a computer big enough, just my computer in my office, right, to do anything like that. So we had to go to Texas to do it. They gave us free time in the Thanksgiving holidays and Christmas holidays and Jacinto Day, right over there. So that's when we could go over there and do it. My first project was a total flop. Simulation of a C2 splitter. I just spent months programming it and modeling it and getting the information from the process and calculating all the parameters and so on, and took simulation to Texas and with my boss, and I spent hours there wiring it up in the computer. And when we turn it on, nothing happened.
Oh, no.
And in that moment, I knew what I'd done wrong. A C2 splitter is one of the largest columns in any chemical process, right? It's very slow. So when you do something, it takes an hour or two to respond. So something was happening, we had to wait an hour or two to see what was happening. And that was useless because I forgot to time scale it. In the computer, you would time scale it, what happened in an hour, you could do it in 5 minutes. But I didn't do it. I didn't realize that that was going to happen. So it was a flop. On the way back to Baton Rouge, my boss, because I was really depressed, my boss saw that and he said, Sharon, he said, people, don't worry about it. He said, people think that Dow is in the business of making chemicals. We're in the business of education. Okay. What did I do to deserve a boss like that? I don't know. At the time, I thought all bosses were like that. The second simulation was a brine pipeline. That was trying to expand their chlorine facilities, and they had to be the brine raw material for Napoleonville, where they had the salt domes. And they had a pipeline 30 miles long, but it was at the limit of the pressure. So somebody proposed to put 3 booster pumps along the way and bring this, that can double the flow through the pipeline and the brine to Plaquemine. So there was concern that when one of the pumps will fail, that the pressure rise and the suction would rise, travel downstream and just turn the pipeline when it got to where the pressure was higher, right? And so we had to find out. We came here to LSU, talked to the civil engineering professors. They couldn't help us because they had never looked at water hammer, which is what's happening there when there was friction. And friction was key to this. So we decided to program it on the analog computer. We had never done that. Of course, it was partial differential questions. So we did it. And we went back to Texas and we programmed it, and nobody wanted to succeed. My boss and my partner, Joe's been at Dow 6 months, I've been at Dow a year then, wanted to fail, so because they was afraid we said, no, it can work, and they installed it and it didn't work, they were going to blame us. But I was, because I'm optimistic, I thought it was going to work because I was confident on the model. Turns out that it worked, right? And they were able to double production, right, and chlorine, and it was a great success, right? So the second one was really great. I had done a lot of one reactor. That was minor. The third project, the simulation of a chlorine compressor, that was expanding the chlorine plant and changing the reciprocating compressor to centrifugal compressors. And so simulated centrifugal compressors, I never controlled them. So we studied that, and that was just a routine success. We knew how to do it. Right. Okay, but the success with the brine line is what decided that we needed a large computer like they had in Texas. And Charlie and I went to Anaheim, California to evaluate a computer that had more computer power than the regular company that sold computers could give us. And I brought my chlorine compressor simulation there and we tested it. Charlie arranged that we work there on Friday, Saturday, and Sunday because I was taking classes from Monday through Thursday at 5 to 6:30. He didn't want me to miss any classes. So we were back on Monday and I made my 5 o'clock class. So we did that. Another thing Charlie did was he never corrected me when I mispronounced a word. Oh, I forgot to tell you that when we arrived here, I was deaf and dumb. I didn't understand English very well and didn't speak it very well. Okay, but he would never correct me. He would just arrange to use the word when he answered me, so I would learn how to pronounce it. Okay, isn't that amazing? The kind of guy he was. Some words I may pronounce with a Texas accent because of it. I started teaching modeling and simulation, right? Dr. Morrow, now a department chairman, 4 years later, hired me as an instructor, so I could reduce the magnitude of my reduction in income. But then I have 3 children. Mary had been born. Okay, and this reduced amplitude, right? And therefore, I started to work on my research project to finish a PhD, like John mentioned earlier. Okay, now, Project Themis was going on. Morrow was a major investigator on a project from the Air Force Office of Scientific Research that involved hybrid computer is a combination of analog computer and a digital computer, right? And by then, at Dow, we have bought a digital computer and connected to the analog to make it hybrid. Well, Project Themis was to do experiments with hybrid computers, and they actually get the funds for LSU chemical engineering to buy a hybrid computer, and the digital computer for the hybrid LSU exactly the same way we put it down. So I had experience on this for this project, right? That's how we got involved here with hybrid computing. Dr. Morrow was the main investigator, and the professors from all the engineering departments working on it. But the hybrid computer was in the chemistry department. Okay, so that got me my job. Okay. Because Morrow was moved to provost. It was clear that somebody with that experience should be hired, and I was hired. Okay. I started to teach transport courses like 3101, which is the fluid mechanics course, and analog and hybrid simulation. And I also taught graduate courses on computer control and on advanced control. And so I use class demonstrations to show the models. We're doing a lot of dynamic modeling and things like that. And I will model reactors and exchangers and tanks and so on. But I couldn't bring them to class. I want to show the students that the models were real, they modeled the real world. So I brought the best thing I could bring, which was a yo-yo. You can see that the string is the same yo-yo I used 50 years ago. I probably stole it from Bernie. He's probably thinking, that's what happened to my yo-yo. So what I would do is this. I would go and develop the model. I had to put some equations in one slide. Okay, just one slide. I do the model. I put it on a blackboard. It wasn't white then, it was black with white chalk. I put up the model and develop the model of the pendulum. Not as a yo-yo, as a pendulum. Pendulum will be more complicated, right? As a pendulum, right? And you can see here, the model is a cosine function. The model is a cosine function, which is an oscillatory function, which means it oscillates just we know that the pendulum oscillates. So there's a cosine function oscillating, right? But the interesting thing is that it depends only on the length of the string. The frequency of the oscillation depends only on the length of the string. Look at this, the mass drops out. And so you only get the length of the spring and the acceleration of gravity is the only function there to the frequency of the oscillations, right? So you can go and easily have the student measure the string. This one is exactly 3 feet, and calculate the oscillations per second, and then time them. You know, half oscillation per second. Oh, see what's happening? Sorry. So they will time 5 oscillations in 10 seconds. And modeling works, right? Then what if we make it half, right? 1.5 feet. The calculation says 7 oscillations per second. And we get that. Or we make it 3/4 of a foot, right? So it says there will be 1 oscillation per second, 10 oscillations in 10 seconds. And it works. Modeling works. It's just a pie in the sky thing. So that's so there's some applications to this. How many of you have ever had to adjust a look at the phone screen here, adjust a grandfather clock? So how do you do it? If it's going too fast, right? You lower the weight and make it slower. If it's going too slow, you raise the weight and make it faster, right? Because the grandfather clock uses the pendulum to measure time, right? There's another application here. Outsmarting squirrels. Son Michael gave me a book for my 70th birthday that had that title, Outsmarting Squirrels. We didn't have this. This is what happened. When I put my feeder, the squirrels will bring it like that, spill all the seed on the ground, and then eat the leach. So I said, what I need to do is make the feeder farther down, right? The squirrels were so confused. So confused that I thought they were saying grace before meals. You have an assignment. Okay, you have an assignment, you have a homework. Next time you go to the playground with your child or grandchild, look at the swings. You'll probably find there is a little child in the swing and a larger child in the next swing. And the larger child will be swinging farther out. So we'll be swinging faster. But pay attention to the frequency of the oscillations. Because the chains are the same length, they'll be the same. They'll both be going back and forth at the same time, but one's just going farther, right? Check that, that's your homework. If there are no children like that, you put your grandchild in one swing and you swing in the other one. All right, so that was what we did. What did we do in the analog lab? Okay, first I started to teach, and these are the analogs we had here at LSU, right, to teach analog simulation, right? And it's a very interesting story behind this picture, okay? My grandson, Roman, saw it at the Middleton Library in the hall way over there in the hall. And he took a picture with his phone and sent it to his father and asked him, is that abuelo? I don't understand why he didn't recognize me. I still look like that. Well, the interesting thing about this picture is that he says down here, that's what he said on the picture over there. He says, chemical engineering courses were established at LSU in 1893 and have always drawn a large number of the international students. Now, most of us here that were here 14 years ago know that we celebrated centennial of the department in 2008. And this year we've been doing it since 1893. Okay? The reason is this. At LSU, chemical engineering developed from sugar engineering. Okay? Because a sugar mill, if you go to a sugar mill, you find most of the unit operations that we study in chemical engineering, except for distillation, all there. And in 1893, the international students being educated were from Cuba. But Cuba was still a colony of Spain, okay? And in 1895, February 24th, 1895, Cuban people started a rebellion against Spain that resulted in the Spanish-American War and liberators from Spain, okay? Well, what happened in February of 1895 is that the Cuban students couldn't come. They were studying at the Audubon Sugar School in Audubon Park in New Orleans, sugar engineering, right? But Audubon has lost most of their enrollment and their money. So the LSU engineering department took over the Audubon Sugar School. Okay. And this is in history of the engineering department in the engineering college at LSU. And so they started sugar engineering at LSU. In 1980 and 1908, Charles E. Coates, the father of Jesse, the one who mentioned at the beginning, he created the chemical engineering department and made sugar engineering a part of it. So until the 1970s, the LSU catalog had two curricula in the chemical engineering department, had sugar engineering and chemical engineering, and you would get two separate degrees, right? And so if you thought that the only contact between Cuba and the chemical engineering department was me, there was something more basic about it, okay? So now, I'm going to show you a lab experiment that we did. I had three here, but I wanted to talk about something else, and so I took two of them out. This was a two pendulum connected by a spring in the middle. It was built in the laboratory, and the students will analyze it and time it and all that, and just simulate it into the computer and find out that modeling is true, right? But the interesting thing about this is you plotted the position of one pendulum versus the other. I'll tell you, what you have here is a bar in the plotter that moves sideways to plot the x coordinates, and a pen on the bar that moves up and down for the y coordinate. When you turn on this explanation, the bar and the pen started running all over the place, as you can imagine, right? But it looked like something is wrong. Turn it off, right? But you notice then that the pen was drawing this plot. Now, is that exciting? Do we have anything today that will do something like that? That's what our computer was doing for us back then. But I want to talk about something else. Back then, this is done differently today. We had what's called a state rally day, in which the top high school students from all over the state came to LSU to take advanced credit exams, right? And then we visit the department, and the department has demonstrations for them. Okay? And what the problem we had in chemical engineering is that the building was so far out here from the central campus that nobody ever came to see our demonstrations. Right? So Dr. Rowley, when he became department chairman, had this brilliant idea. He rented a ballroom in the Union where we could bring your demonstrations over there and show it to the students. It was brilliant. The students will come out like a right into our demonstrations, right? And and a graduate student, no, not a graduate student, called Dwight Fontaine and I were going to do an experiment to show the students with another computer. And a professor called Dick Farmer had a book with the description of this ancient Chinese game of Nim. It says that Nim was the Chinese for takeaway. It was played with several piles of items, and each player will just take turns in taking as many items from one pile as they could, as they wanted to, right? And then as they wanted to, and then there was a strategy for winning, described in the book. So the other computer had logic components that we use to simulate safety override systems. The logic program has two signals, two values of the signals, true or false, and three computing components, A or B, A and B, and not A, right? So only three things you can do with them. We could program the logic to win at NIM, okay? So we built this box as an interface to the computer. We used it with checkers. We had 3 piles of checkers, right? And with these dials here, you could enter how many checkers in each pile, and then the wiring that we did will convert them to binary. So this was 7, 6, and 5 in 3 piles, right? That's how we started the game. We took those 9 signals to the computer, did the programming, and brought back 3 signals to turn on these red lights. And the red lights allowed us to do the best play every time, right? So the problem was, who do we get it to play this game? High school students are not going to want to play against a faculty member, right? Or a college student, right? So we had to hire somebody, right? And we found the perfect person. It was this young man who just turned 6 years old. Okay. No, I have to tell you that the machine there was wired by Carlos Moreno. Where did Carlos go? Carlos Moreno, and you know how neatly he did it. But he was an undergraduate student, so this was free labor. This young man was also free labor. He was our son Bernie. Okay, so we didn't pay him. But let me tell you, I've done this for Super Science Saturday, and it's tiring to stand there doing the demonstration over and over. And he never complained. He was so happy beating those high school students. I may have bought him a hot dog and a Coke, I'm not sure. It was amazing. We hired him again at no raising salary when it was 7 and it was 6. All right. So I'd like to tell you about this, so I didn't tell you about the other stuff. Okay, sorry. Okay. There were 2 other demonstrations I used on our computers. A missile intercept. We were 20 years ahead of the Patriot missile, right? And safe landing on the moon. The students could turn in with a switch, the rocket, and get the lunar module come down there without crashing. And that was a very interesting one that we had to do. So what did it have to do with chemical engineering? Nothing, but we were the only department with analog computers. The next phase is process control. My main expertise, right? I did most of my research was process control, and I say I was teaching graduate courses on computer control, and I was teaching advanced control and so on. But the undergraduate course was taught by other professors because it's a fun course to teach, and they like teaching it, right? So I was a teacher the other course. So, but in 1984, IBM granted us, by then the American computer had disappeared because digital computers get faster, they got, memories got cheaper and more abundant, and the algorithm to solve differential equations got better. So it kind of replaced analog computers and they disappeared, right? So the average computer disappeared. When in the same place we put this mainframe computer IBM donated to us for us to teach a program they marketed called the Advanced Control System to control chemical process. Exxon used it overseas, and at least one plant here that we visited, the Goodyear plant just outside of Beaumont, used it, right? And they gave it to us so we could teach the students about the advanced control system. So what we did was we added a 3-hour lab to the analog, to the control course. And then nobody else wanted to teach it. So in the 3-hour lab, I developed exercises, simulations only in ACS, and then the control only in ACS, so students could learn how to do computer control hands-on. And in those labs, and then I taught it for 8.5 years. Nobody else. Eventually, the mainframe got obsolete because everybody was having PCs on their desks and things like that. So this disappeared, and then I want to teach plant design. So, but I taught a short course for IBM in Rio. It's a Fenelon, you see it, right?
Yeah.
Fenelon broke his book, which is a book that John talked about earlier of Smith and Corripio, in Portuguese. He has a book in Portuguese, and he brought it with him. Yes, and he's studying it. Right? Yes. So IBM invited me to teach this course 4 times. Went to Rio and 1 time to Sao Paulo, and so I did that. We didn't have any opportunity to go somewhere like that. And we also went to the University of Negev in Israel to teach the course once. But I'll tell you this. I took my wife to Rio. Why did I do that? At that time, actually, I was teaching short courses around the country for ISA and for ASCHE. And I would take her with me to New York and Toronto and Los Angeles and Louis, everywhere. I took her with me. The reason is this: when I was an assistant professor, I went to present a paper at an Air Force sponsored conference in Honolulu, and I didn't take her. When I came back, she had been buying furniture. The money I was trying to save. I didn't want that to happen again. I did not take it to Israel, though. Okay. That's it in Israel. Okay. Then we went to process design into the 90s and the next millennium, right? Why did I do that? What made me do? Okay. Let me go back. Now, when I was full-time there in '66, I was asked to develop a simulator for a chlor-alkali plant, a new chlorine plant that was supposed to be self-contained, have its own power plant to generate the chlorine for electricity for chlorine. And another chemical engineer, Enos Bonham, and me were assigned to develop the simulator to simulate a cogeneration gas turbine combined cycle power plant for the plant and the multiple effect evaporators. Chlor-alkali produces chlorine and caustic, and the caustic requires concentrating the material from the evaporators, right? From the cells, right? So we did that, and Enos taught me a lot about process design, about Fortran programming. Fortran programming was another one of my obsolete skills. I was really good at it. It became obsolete. Okay. The analog simulation and a lot of others, okay, a lot of others, the slide rule. Now, we did a simulator and I kind of like it. In fact, but I had to go back to control the DAO. They loaned me to do that for a couple of months. We had, for the first time, we're going to use a remote terminal to use a computer in Houston. We had to go to Houston to test it. And I had to go the day that my wife brought our daughter Mary from the hospital. I was in Houston. Yeah. So then in '77, when I was consulting for DAO in summers and Christmas, they gave us a assignment to simulate a coal gasification plant, right? And I did it with this other PhD from the University of Florida, Dave Britton. Yeah, this is Dave Britton and me. These are another graduate from the University of Florida. And the two of us did this project, and it was very successful. We actually understand that the simulation was used to design the plant and to run it for 10 years under a subsidy from the Department of Energy. And at the end of 10 years, the subsidy disappeared and the plant was not economical, so they shut it down. But our simulator was used to design it and run it. So that was great. Okay, then that got me so excited that I said, okay, I want to do this. So I applied immediately for my sabbatical when I came back, and I applied for to go into the Aspen project at MIT. I was accepted, and I was there for a year with my family. And so that was a great experience, right? And that people don't remember this because people use Aspen Plus. Aspen Plus is where they got the team through the original Aspen program and develop it to make it commercial. But the Aspen original was funded by DOE, and they want to evaluate proposed coal gasification and liquefaction processes. And when I did this slide and I looked at it, I said, many of the young people in this audience are not going to have any idea why was DOE trying to gasify coal or liquefy coal. But the concern in the 70s, after the big energy crisis with car lines at the pumps and no gas anywhere, they decided that we're going to run out of oil and gas, and that our hope for our energy requirements was extensive deposits of coal that we have in this country. So that's we say the coal has to be gasified and liquefied to use in cars and power plants and things like that, right? No power plants, but other plants. So then we're looking at that. We're spending all our money doing that, right? Who would tell us that 45 years later, we're essentially getting rid of coal and we're about to plan to get rid of oil and gas, right? Amazing, it? The concerns change, no doubt about it. Okay. Another thing that convinced me to do plant design was a computer-aided process design conference in Sonoma, Colorado. I took my wife there. And so a paper by Professor Douglas. Most of the papers were people saying how they're going to program computers to do the entire process design, to do the material balances, the sizing of the equipment, the costing and optimization, everything. Just press a button, a computer does it all for you. He gave a paper on how he does it. He does it by the back of an envelope. This is the cover of his book. Back of the envelope, he says, you do a process design like an artist designs a picture. Right, you first outlines it and then fills in the details. So that's what you have to do. You start by outlining the process, and you do that with material balances. And when you do that, then you start adding the simulation, and then you add the sizing and costing, and then you add the optimization, right? You add the details. And all along, he says you have to evaluate the economics of the process as best you can. Well, I decided I want to teach plant design this way, okay? The way Dr. Douglas wanted, different than all the other professors that were there at the conference. The FOCAD conference, Foundations of Computer-Aided Process Design. Okay. The first plant design that I did that time, I got it after Dr. Johnson finally retired from teaching plant design. I was able to start doing it. His daughter is here with her husband, right? And he retired also, kept the teacher for a few years, and then went to work for Exxon, right? Yes, right. So my first one was a quasi-flop. I didn't realize the student didn't know how to do material balances. So I gave them an assignment in material balances and they couldn't do it. At the end of the course, a regulation went to the department chairman asking that I will never again be allowed to teach plan design. Now, I taught it for 20 more years after that. Nobody else wanted to teach it. I was supposed to teach in the curriculum, right? So I was safe, all right? But that was the thing, but with quasi, because you see, we're always trying to get the students to participate in the ASCHE National Design Competition. I'll give them the project, the design competition, I had to do in 30 days, all by themselves. Well, they could do it in teams, I let them do it in teams, but to send it for competition, they had to do it by themselves with no help from professors or other students or so on. And nobody wanted to do it that way. They wanted to do it in teams. So I could never get them to send one for competition. But this year, the first year I taught it, they had an alternate, a team competition. It was called the plastics recycling competition. And I said about two of the teams decided to do that instead of the regular one. And I sent them in, and one of them came in third nationally. These people here, Costa, Gwen, and Zoo. And they had to go defend it at the ASCHE conference in Seattle, and I went with them, right? So that was quasi, it wasn't complete flop. Some success, right? Now, the year after was the best plan design class ever, right? So, was it a BASF that I said, this was the best class? And one, oh, it wasn't that class. I wasn't. Okay, these are some of the people. Rod Wenchen, I think his leadership, he was the chair of the ASCHE student chapter. I think his leadership has something to do with what the course work. But the women, Sharon Hogan, please shout. Sharon Hogan, Tricia Como was the third of three girls from the Charles that were at the top of the class as they went through. And she was the last one, the third one, the youngest. And I met their father. The father was manager of the PPG plant in Lake Charles. Sarah Beth Cubillon, couldn't come. She has children, she lives in Ohio. And their gang, right? And one of those students invited me to the graduation party in Lafayette. So I said, oh, I'm now teaching the seniors. This is going to happen all the time. So turns out in 30 years, it happened one. Is Indian Rose mostly here? I guess he couldn't come. Okay, she invited my wife and I to her beautiful wedding at the Northern Plantation, right? And so that was great, right? But it didn't happen again. Right? I did have Carl North was the department chairman. He didn't like to go to the diploma ceremony, so he delegated to me. So we'll go there to congratulate the students that were getting the diplomas, and I got a lot of smiles and hugs as they went through. So that was almost the same as the graduation party. That's what happened. One of the students in that class, Armando Leaching, was very active in the local section of ASCHE, and I was active too, so we worked together. But he passed away earlier this year. Yes, unfortunately, yes, right. Okay. Why did I teach leaching? Okay, my colleagues tell me, don't teach them leaching. They're never going to do a leaching project, a leaching design, right? And so that never bothered me because I never, in school, they always told me about generation, gas turbine combined cycle power plants, right? They never told me about that. So that's what I had to do. So, Dr. Boyle told me a story once that a student that was visiting the department, I'm very appreciative of the education he got here. He told him, you and the other professor taught me how to think. And that gave me the idea that Dr. Boyle was trying to ask me, that's what we're doing. We're teaching the students how to think like chemical engineers, right? And so that's why I teach leaching. I'm going to show you how. I teach them how to think, okay? So I have a recent demonstration that I do for the class. when I was teaching plant design in the spring, I was teaching unit operations in the fall. That's where I taught leaching, and I did this demonstration, right? And one student that really appreciated, we told me in an email, was Kurt, Kurt Ristrup. Sent me an email and said, when I become a professor, I'm going to do drills and demonstrations. Okay. And he's a professor now at Purdue. Okay. All right. So this was the equipment. I had a bottle, some colored water, and 3 cups with 30 cc's of water, 10 cc's in each of the other 3. I would just pour the colored water in the bottle and put it back, and then rinse it with this. First, I will rinse it with the 30 cc's, right? And then I'll go and put the colored water again and rinse it 3 times with the 10 cc's. Okay. Now, some of you here may know exactly why, right? But some of you may think, same amount of water, no difference. Well, it says, maybe a little bit better, but no worth the effort, okay? Let me tell you, this is how it happens. The first time we add 30 cc's, I assume there is 1 cc of water, of the colored water left, or whatever you're rinsing, where it could be milk, it could be juice, it could be syrup, whatever. You add the 1 cc, you add 30 cc's, and you get 31 cc's, and you rinse, move it really well so they will get all to the same concentration, and then pour out what's in there, and you have 1 cc in there. All right. What's the concentration? It will be the original concentration divided by 31. Because I will use it from 1 to 31, correct? Everybody can follow that? Do we continue to follow that? Okay. All right. So now we're going to do it 3 times with 10 cc's each. The first time we add 10 cc's and the concentration drops to 1/11, right? Then we do it again. We reduce it by 11 again. So that means that now the concentration is the original divided by 121. And then we do it a 3rd time, and it's original divided by 1331. The last 1 cc left in the bottle, right, is pure water. What does this teach us, right? What does it teach us? Quantitative thinking, right? Quantitative thinking, right? Very simple experiment, and so we need thinking from that. My son Bernie claims that his success in troubleshooting process problems was because his ability to do quantitative thinking, right? And I think there is very little quantitative thinking going on in Washington, D.C., California, in California, right? So that's what I was teaching with Leaching. Okay? Now, I took the students to see in the sugar factory, the mills of the sugar factory operate as a countercurrent leaching operation, continuous leaching operation. What you do is you squeeze the fibers, and the last mill, sometimes it's 4 and 5 mills, because you have to take all the sugar out of those fibers, right? So they put hot water and collect, squeeze it out and collect it, and then pump it back to the previous one, which is and then leaching is removing chemicals from solids, right? Basically. So you take it, it's a little more concentrated now, and then you take that and put in the previous one, and then you get the mixed juice, which is final juice that's going to be processed. And that's how it works. I took the glass to the Cinclare factory across the river here. It's no longer there. And they're going there, and they're on top of the mills, watching the water going in. I want them to see that, right? And this here is my friend, Rogelio Piñeiro, the most ingenious person I have ever met. He passed away 6 years ago. He was the most ingenious person. My father was very ingenious and told me a lot of things, but he was very ingenious, right? I would take my classes on control there and show them. He had his own inventions, how to measure the juice, the mass flow rate of the juice, very inexpensively, continuously, because before he was there, they would put them in batch, fill a tank and wait, and fill another tank and wait. He did it continuously with very simple instruments, right? And the other thing, you have to add a lime slurry to control the pH, and he figured a device to do it so it will not plug up because it's a slurry, so it plug up any control valve. So he had a device, and you could see it operate. You could see how it operated. The students could see how that device divided the lime to control the pH. So it was amazing. He will take the students to the multiple effect evaporators, take them to the last effect, where from a last port you could see the solution glow boiling. Okay, and he said, touch it, it's not hot. So they would go and touch it, and it wasn't hot. It was like 120 degrees or something like that. And he said, you know why? Because of the pressure. See the gauge there? It's very high vacuum. That's the reason it boils at very low temperature. I mean, he would teach them to us all kinds of things. He came up with a computer algorithm to determine, this will be surprising to some people, the separation of the sugar from the molasses is used in a 3-stage countercurrent process in which each stage is a vacuum pan, which is a batch process. 3-stage countercurrent process, with each is a batch process, and you have to determine when the batch is over, right? And we have to hire these punteros. They made a point at which the batch was over from all over Latin America to come here, get them the visas, pay them the salary, so they would tell us when the batch was over. He developed computer algorithm to do that, measuring the temperature, pressure, temperature rise, and the viscosity, and so on. He would do that, and I had 3 different algorithms for the 3 different stages, right? So it's amazing how ingenious it was. I met him when he called me on the phone and said, I'm trying to learn computer control, and I don't know anything about it, so do you have any references? I said, okay, I have a bunch of books I gave him in my graduate class, so I sent it to him. Next time I visited him, he had in his shop, he had all those books. He had bought them all. He was an amazing guy. An amazing friend. I also took the class to see the process that they were designing. The university would loan me a van to take them. And then this was a class in 1995. I went to see the phenol class at Georgia Gulf, phenol plant at Georgia Gulf, right? The university stopped giving me the van, so the students had to drive themselves, and they started to go. Fewer and fewer students were going, so we had to stop it. Okay, I have this demonstration. Last demonstration, okay? What I have to do. So let's see. See the sound what it worked before.
The purpose of this experiment is to show that just like a liquid doesn't burn unless vapors form a combustible mixture with air, the candle doesn't burn. It's the vapors from the candle that burn. Okay? This is a very nice trick. You can do this to your grandchildren eventually, with your children. Okay? Okay. So, the temperature in which the vapor pressure of the vapors above the liquid form a combustible mixture with air. Just as in the candle, it's not the wax that burns, the vapors can be burned from the candle level.
Okay, all right. Yeah, so I used to do this in class, but with the COVID, I had to record. What is the purpose of the wick? Okay. The candle would not light up without a wick. If you put a match to the candle, it would burn, melt, right? So the wick allows the molten wax to rise to the top by capillary action, and then they vaporize and burn. Right? That's how the candle works, right? Have you ever heard the number from the musical Godspell that goes like this? You are the light of the world. You are the light of the world. But the tallest candlestick ain't no good without a wick. You have to be bright to be the light of the world. So I do this and I tell the students that they are the light of the world. You are the light of the world. I believe that there are more good people in the world than bad people. Don't pay attention to the news. I don't. So, and I tell them, but for you for your goodness to show, you have to let the light shine, right? You have to help those who need you, right? The poor and everybody that needs your help, right? So do something for somebody. And as Professor, what's the name, Buscaglia says in one of his videos, says, and don't ask me what is there to do. If you do, I'll strangle you. So I do this, and and the whole thing of the candle is to get to him. Right? I can sing a little. A little bit when I was singing from my daughter-in-law, Lacey. She's a great, outstanding singer, right? So this slide is the one that I showed the class, the last slide in the last lecture, right? So I want to show it to you. There is an energy in us which makes things happen when the path of other person touch ours. I don't know how many students that touch my mind, right? So, and we have to be there and let it happen. When the time of our particular sunset comes, our things, our accomplishments won't really matter a great deal. With the clarity and care with which we have loved others, we'll speak with vitality of the great gift of life we have been to each other. And these are some of the students that have run into my path here. This is the design class of 2014. Is that Ryan here? He said he was coming. Hey, there's the Ryan. See? Here's the Ryan when she was younger. Okay, and this is Lori Stout. I don't think she's here. Lori Stout is over here. She's in the Charles. I met her in the Charles at my daughter's house before she graduated, right? So this was the class, the last class of the semester. This was the unit operations in that same year, 2014. And these two students, this was Halloween day. So these two students are dressed as Dr. Lurito. Okay, so let's see, this is the 2015 class, the unit operation class. And our court Ristref is not there because he's taking the picture. These are his papers right here. Okay, this was what I call the St. Aloysius gang. These 5 students started at St. Aloysius in preschool. And for 18 years, they stuck together until they graduated together in chemical engineering. Yeah, they're Margaret and Rebecca and Austin and Kurt Ristrup and Anne. Okay, they're amazing, amazing students, right? This was the first class in which I had them show that they're the light of the world. It was 2018, and it was the second 2019. Okay, and after that, the COVID stopped doing the. I had to stop doing this because of the COVID, right? Students didn't come to class. So it's amazing that they paid me a salary for doing this. It's also more amazing that I took it. So, and it's, you know that they let me teach ethics. Let me teach ethics to the students, so you can imagine. So bye-bye and thank you very much.